Okay, so what I want to do now is say something about quantum mechanics. We'll be covering that in more detail 2 lectures from now. So quantum mechanics. And quantum mechanics was really developed, somewhere between well, it took several decades to develop quantum mechanics. And I'm putting down 1900 to 1930, although you can argue a lot about different dates. And Einstein, Podolsky, and Rosen in 1936, said that quantum mechanics, they published a paper that was really saying quantum mechanics is incomplete. Is incomplete. And the reason, well, let's put this in quotes because people don't believe this anymore. The reason is you can take 2 particles and they can have opposite momenta and opposite positions, x and minus x. And these particles, so you can prepare these particles so that whenever you measure their momentum, they're opposite. This is minus p and p. And whenever you measure both of their positions, this one is at x and this one is at minus x. And you cannot measure the position and the momentum of the same particle because quantum mechanics says that this is impossible because the position and momentum are conjugate variables. And we will, well, we're not going to be using continuous variables, but we will explain what happens with discrete variables at some point later in just a few lectures. So that means that, well, this particle must have a momentum because if you measured this particle, it will give you that momentum. And this particle must also have a position because if you measured this particle, it would tell you about this position. But quantum mechanics says this particle cannot have both. So there must be some information this particle knows that quantum mechanics doesn't tell you about. So quantum mechanics is incomplete. And what Schrödinger says, Schrödinger replied to this by just saying, no, it's not incomplete. These particles are entangled. And that's just the property that entangled particles have. So maybe this wasn't really satisfactory for Einstein. Or actually, Schrödinger said they were Verschränkung and not entangled, but what happened in 1964? Bell proved that no classical explanation for the behavior of EPR pairs. EPR, I should say, because Einstein, Podolsky, Rosen came up with this pair of particles, an EPR pair is what they're called. And Bell proved that there's no classical explanation for EPR pairs. So if quantum mechanics is incomplete, it's incomplete in not in a classical way, but in a way that gets even weirder than quantum mechanics, which I don't think would have satisfied Einstein at all. And in fact, these, I don't have the date, but 1980-something, Aspect showed Bell's predictions were correct. And people have been improving Aspect's experiment. I mean, when Aspect showed Bell's predictions were correct, a few very doubting people said, but what about this loophole? What about this loophole? There could still be a classical explanation. And people have been closing these loopholes ever since, and I think they're pretty much all closed now with the latest experiments, which just happened in the last few years. So there's no classical explanation for quantum mechanics. So quantum mechanics is really weird. And now I want to talk about what happened next. So in 1982, Herbert, in a respectable physics journal, published a paper called Flash, First Laser Amplified Superluminal Hookup, which is really faster than light communication. Communication using weird properties of EPR pairs. Communication using weird properties of H, hookup. H is hookup. Obviously designed for the acronym. Using weird properties of mechanics and EPR pair. Properties of QM and EPR pairs. Now, one of these referees of this paper was Asher Perez. And Asher Perez said in this referee report, well, this paper has to be wrong, but I can't understand why it's wrong. So why don't you publish it, and we'll see someone come up with the flaw in the paper. So this paper is indeed wrong. But in 1982, two groups of people looked at this and figured out why the paper was wrong and published the no cloning theorem, which we will get to, which says that a single quantum state, actually, technically I should probably say a single unknown quantum state, cannot be duplicated. So how much of this theorem is due to this, well, Berkeley hippie who, who came up with this wrong paper. Well, it probably wouldn't have been discovered in 1982 if he hadn't published this paper. It probably would have been discovered eventually. So now I want to get to, okay. So in 1985, David, oh, no, let's go back to 1982. Feynman and simultaneously in the Soviet Union, Manin, but a year or two earlier, said very difficult to simulate quantum mechanics. Mechanics requires 2 to the n, I guess, resources or time for n particles. And then they said quantum computers might be faster. Well, they said would be faster. So use quantum mechanics to simulate quantum mechanics. Yes, order of 2 to the n, or I should really say Cn, because it's not, well, depending on exactly what you mean, it's exponential, but I mean, this is a very vague statement, and depending on how you make the statement precise, this time bound might be more or less. So it requires 2 to the n complexity to simulate n particles. Computational steps is really complexity. And we'll say more about this. We'll say more about what complexity is in next lecture. So what happened after that? Well, David Deutsch described a quantum Turing machine. Quantum Turing machine. Said it would be good for simulating quantum mechanics, although he didn't go into any details. And when you do go into the details, it's much more complicated than it sounds at first. And asked, is it good for classical computing? So this is the first, I mean, Feynman and Manin, if a quantum computer is better at simulating quantum mechanics than a classical computer, maybe, I mean, why shouldn't it be better for classical problems than a classical computer? It's not clear that anybody before Deutsch asked this question. And really, in this paper, he gave some very, very unsatisfactory answers. But in 1982, Deutsch and Jose said yes. Sort of. So much less unsatisfactory answer. And after that, people really started thinking about quantum computing. And Bernstein and Vazirani. in 1993. And in 1994, Simon came up with a problem that is exponentially faster on a quantum computer. On quantum computer. And roughly this is where I came in, because I was on a conference program committee where he submitted his paper, and unfortunately we decided to reject it. I have the satisfaction that I argued for its acceptance, but I mean, in retrospect, I clearly should have been jumping up and down demanding that it be accepted instead of just, you know, instead of what I did, which was much less demonstrative. But yeah, and this uses periodicity. So I had the idea, well, periodicity might be important. Discrete log and factoring, which are very important classical problems, use periodicity. So maybe quantum computers can do factoring. So in 1994, actually, I guess Simon's paper was written in 1993, but not published till 1994. I think I saw it in January 1993. Factoring and discrete log. Log on quantum computer, 1994. And this is really where the field of quantum computing took off. I mean, before 1994, it was a bunch of people that most physicists thought were kind of a little bit crazy. And indeed, some of them really were crazy. Looking at it, and in 1994, after the factoring result, everybody started thinking about it. And then in 1996,
Can I ask a question about so the 1996 Simon thing? It's not clear that, for example, simulating quantum mechanics is in that category of where a quantum computer would be exponentially faster than.
Oh no, simulating quantum mechanics is okay. So it's not. It's yeah. So it's simulating quantum mechanics is not provably faster, but it's clearly faster. But I was. You know, this is the question: is quantum computing, are quantum computers good for classical computing? Is this thread? I think most people were agreed that quantum computers were better for simulating quantum mechanics than classical computers. Although, you know, since then, people have discovered algorithms that really work well for simulating some quantum problems that people didn't know how to simulate before then. So classical computers are getting better at simulating quantum mechanics too. So yeah, in 1995 or so, Love-Grover came up with his search algorithm, which searches a space of size n in root n steps. And after that, you know, well, that's as far as we're going to do for algorithms in this class, because these are all very easily presented algorithms that are very important. And since then, most quantum algorithms are for less important problems and are much more complicated than these.